Hello, welcome to our quantum simulator tutorial. So why do we need quantum simulators? Of course, we need them to generate new algorithms. Scientists don't always have access to high-end devices, and they don't always have access instantly. And there is more like symbolic milestone. We want to demonstrate that quantum computers are indeed meaningful to humanity, that we can simulate larger circuits on quantum devices than on ordinary computers. And we want to help these quantum devices to help them develop faster and more reliably. And this is also how quantum simulators can help us, because we want to verify the correctness of our physical device by comparing it to the perfect simulator. There are several types of quantum simulators. The first is the simplest one, is when you store a vector of numbers, and each complex number it represents a complex amplitude. Then you apply gates one by one. You kind of evolve this state vector through time, and then you end up with some state vector that is the resulting state of your system. Then you want to generate your measurement output. You just random sample from this distribution. This approach is fine and it's very easy to implement, but it has a very huge drawback. The state vector, the number of entries in this state vector is huge. It grows exponentially with number of qubits, and I think you probably all know that. And there is a workaround that called tensor network simulators. They they don't store a full state vector. They evaluate tensor network. They convert the circuit to a tensor network, and then they contract the large circuit one by one without storing the full state vector, but rather storing the information in the form of tensors. And also, there is a lot of study inside of tensor network simulators. There are differences between them as well, and most of them is how do you contract the tensor equation? What is the ordering algorithm for your tensor expression? And of course, there are noise simulators. Let me move myself a little bit. Of course, there are noise simulators, and they are mostly for simulating hardware and providing experimentalists with the reference that they want to compare with. Argonne National Laboratory develops Argonne National Laboratory develops several kinds of simulators. There is state vector simulator, Intel QS. There is Qtensor that I'm lead developer of, also made under Argonne, and also there is noise simulator Quark. We will be talking about, of course, the second one. So our Qtensor project is an open source project, and the code right now is open source on GitHub, and I believe on PyP, but it is not the most recent version. And we try to be it as easy to use as possible. Of course, there are complexities that come from the problem itself, but we try not to introduce another complexities. And we, of course, want to be our simulator as fast as possible and as easily parallelizable as possible. And we plan to run this simulator on supercomputers. This simulator will probably be used for verification of quantum supremacy using QAOA and other algorithms. So let's start with what are tensor network simulations and how do they work? For that, we need to know what a tensor network is. And for that, we need to know what a tensor is. So tensors are generalization of matrices. Of course, matrices, everybody knows what it is. It's just a square table of numbers. And what if we have another dimension? What if we have a list of tables, like a sheets on spreadsheet? Well, we can say that this is a three-dimensional array of numbers. This is a rank 3 tensor. What if we have rank 4 tensor? Well, this is an array of rank 3 tensors. So you always, when you have a repeated structure of rank r minus 1, this means that you have a tensor of rank r. And so what is a tensor network? Tensor network is composed of tensors that are joined by some indices of those. So when you have a vector, this means that you have only one variable, only one index, and in tensor network notation, this picture is represented by a single node in your tensor network and a single edge that corresponds to your index. Then if you go one dimension higher, you have a single node that is your tensor, and you have two dimensions that are your indices, two edges, sorry, that are your indices. And you get an idea. The higher you get, the more edges you have for a particular node. Now, what it means to construct a tensor network, well, sometimes you want to evaluate a huge expression that has a large number of tensors, and those tensors are, the expression has a summation sign over some particular indices. And this is usually, this is a representation of some complicated systems. It could be a probability model, or it could be a quantum circuit. So here we have two tensors that are joined by index j, a and b, and they are equal to tensor c. But you can get the values of tensor c by contracting tensors a and b, by summing the products of these entries. So you have entry a ij multiplied by entry b jk, and then you sum over index j, and what you get is the entry of cik. And you can have complicated structures in your tensor network expression, because this linear thing it's just a matrix multiplication. It's not very interesting. But if you have very complicated expression, very complicated model, you end up with complicated tensor networks. So, okay, we want to contract tensor networks, and what is that bottleneck that kind of prevents us from doing this for any kind of tensor network? Usually, contraction of tensor networks is a memory-bound problem. This means that you are most likely to end up of memory than you will end up, being not very patient and just stopping your simulation. So let's see what we have when we contract one edge. Here on the left-hand side, you have two tensors A and B, and they are both of size 16. They have 4 indices. Each index has dimension 2, and hence they have 16 entries inside of them. What happens when you contract them? You merge those two indices, you remove that edge, and the resulting index has 6 edges, which means that it has 2 to the 6, 64 entries. So the number of total entries, the number of total memory, it was 2 times 16, 32, and it doubled. And in general, when you have, so what if you go from 4 edges per tensor to higher number? So this is what this formula says. If you have 2 tensors that have 4 edges, you double your memory after contraction. If you have 5 edges, you will quadruple your memory after contraction, and so on and so forth. So how do we represent gates as tensors? This is quite simple. let me show how QOA looks in this representation. This is the simple QOA circuit that has only 4 nodes, 4 qubits. And for tensor networks, it's very important to find the order in which you eliminate, in which you merge those tensors. And to find that order, we use what's called a line graph of tensor network. And it is complicated, rather complicated aspect and a rather complicated concept from graph theory. But let me show you a very fun animation of what a line graph is. Here, I have a bunch of files which are Bristol cone circuits. They are not called QOA circuits, and they have, I'm not sure how large these have, but they have somewhere larger than 30 qubits. So we load this file. This is a simple web application that I wrote to visualize, kind of to feel what are those contractions like. So you load this file, and this is in fact the line graph of a tensor network. And in line graph representation, you can construct indices by merging their neighbors. So let's merge. Let's eliminate this index Q7. Just clicking 2 times on it, and you see that all the neighbors are connected. And the key part is to find the order of removing those indices, so that you will not end up in a large, fully connected graph. Like you see, when I contract these guys, you will eventually end up with a very connected subgraph, and every connected subgraph represents a huge tensor. So let's see what if I contract this tensor. I believe it's tensor 15. A lot of neighbors are going to be connected, and this already huge clique will be even more large. And the very hard, in fact, in P-hard problem of finding the elimination order is finding the optimal contraction order. Okay, so that's it for theoretical introduction. Let me show you how to use our simulator. It is called Qtensor. Well, on this slide, I first start with importing Qiskit and printing the Qiskit version, so you know which Qiskit version to use. And in fact, beware that Qiskit in later versions, they broke something with their QOA, and the energies are not correct. So I recommend using these versions. Let's go ahead and generate a random graph. We will use Erdos graph, and this is approximately degree 3 random graph. And let's build a QOA circuit on this graph, a QOA ansatz state. So Qtensor provides universal interface for building circuits. So for example, here we imported here from Qtensor, we imported Cirq QA composer and Q3 QA composer. These are all classes of that inherit from QA composer, and they are very similar. They just basically swap the gates that are used to compose the circuit, and we can see that, well, first you generate a P equals 1 circuit for ansatz state. Let's see how you provide the gamma parameters and you provide the beta parameters. In Qtensor, they are ranged from 0 to 1, not from 0 to pi. But, well, Qtensor is under active development, and probably that will change. Let's generate Qiskit circuit. We just import Qiskit QA composer from Qtensor, and we use it the very same way we used it before. We pass the graph, the gamma and beta, and we just take the ansatz state. The returning value, the Qiskit, the composer.circuit will be your circuit of type that is specific to your backend. And let's simulate circuits. So here, Q3 is basically a backend for tensor networks that Qtensor uses, and we will be using Q3 simulator. And in fact, there are Circ simulator, and I think there is Qiskit simulator, which have all the same interface to simulate the circuits. And this is very useful, for example, for comparing the benchmarks. Let's see how that state looks in Q3. And well, it's not a very special object. It's just a list of gates with the qubit that is inside the gate, the qubit that it applies. And yeah, so here is how we simulate using Circ. We create a simulator and we call a simulate method. And we pass to this simulate method circuit. The resulting object is dependent on backend. It is in fact what the Circ simulator returns. So you should use the API of Circ to access to final state. If we want to simulate several amplitudes in Qtensor, we want to use simulate batch, which is specifically because we use tensor network approach. The simulate is equivalent to contract, and if we contract full tensor expression, if every node is eliminated from our tensor expression, this means that we are left with a scalar. Scalar doesn't have a dimension; it's just a number, and this is a single dimension. Well, if we want to simulate several amplitudes, we want to leave out some dimensions at the end of our contractions, so that the object that we are left out is a tensor that we can reshape into our state vector. So this is why this method called simulate batch, and the sim object is the Q3 simulator. So we pass this simulate batch method the circuit that we used. So the com object is the Q3 composer, and the circuit is just an array of gates. So this argument batch vars means that what are the variables that we want to leave out. And well, it happens so that those batch variables, they are labeled from 0 to 1, and we want exactly them. The first variables that were created are the qubit variables. So let's plot the state. On x-axis we will have real component. On y-axis we will have imaginary component. And so this is the line here is the like a phase diagram of this state, of this quantum state vector. And let's plot as dots our circ, and we can see that they are indeed very close. So there is a very useful technique for simulating QoA, and in fact, I think that I should show a slide about this. Light cone optimization allows you to cancel out most of the expression in your tensor network, because when you do the QoA algorithm, you want to calculate energy. You don't want the unz state. You eventually want to optimize the energy, and for that, tensor network simulators are very useful because they allow you to calculate not only the probability state, they allow you to calculate basically everything that you can get from a tensor network. And light cone optimization is where you cancel out all the gates that are from one part of unz state and from conjugate part of unz state. You cancel out those parts that are irrelevant with respect to your particular part of cost function. The cost function for QoA is sum over different edges. Here, this is the summation inside, and the operator that you sum over, those are local. They act only on 2 qubits. So you want to consider only a small subgraph that is centered around those 2 qubits. And let's see how do we use the light cone optimization. We have to use a QoA composer, and again, we can use just energy expectation light cone and pass the edge that you are interested in. And this way you create the circuit on the composer.circuit object, and then after that you can just simulate your object. If you want to simulate the full sum over all the edges, then you can use QoA Q3 simulator, which has handy functions to generate those light cones and simulate them, and then the sum is what you're left with, and the API is very similar to that of that you saw in just a plain simulate. And you can use, of course, Qiskit circuit as input. For that, you will have to import something from Q3, a simple conversion method that allows you to convert the Qiskit circuit to Q3 circuit, and then there is a small line that converts Q3 to the format that allows you to simulate. In fact, it's just a flattening an array. And let's go to the optimization part. So optimization is finding the perfect order that allows you to have that good performance. And let me pause a little bit here and just show what numbers do we have for optimization. What is the behavior of this optimization? So we have the numbers for QoA of degree from 3 to 5 and from p equals 1 to 2 for all degrees, and we have p equals 3 for degree equals 3, and these are just seconds for notice the 1000 node graph. And well, this is pretty impressive. Usually people are used that quantum circuits cannot be simulated on larger than 30 or 40 qubits. Here, using light cone optimization, we can easily simulate 1000 node graphs, because the circuits that we use are the subgraph circuits. They are constructed from a less number of qubits. And the interesting result is described here. If you change the size of your graph from 1000 to half of that, or to half of that, you will in fact increase the complexity of simulation, because your subgraphs will become more complicated. There is not an even distribution between those subgraphs. And in fact, it is harder to simulate 30 or 60 node graphs than 1000 node graphs, which is what you can see on this picture. The contraction width is exponential. The simulation cost is exponential with contraction width. So in fact, this is equivalent to looking at logarithmic graph of simulation time or simulation memory. And these are how the subgraphs look for degree 3 random regular graphs. If you have 1000 nodes, the structure looks very much like a tree. If you have smaller nodes, you have loops, and those complicate your tensor expression. The ordering algorithms have to do more job to find a good ordering. So let's see how we run this one ordering algorithm. We can look at the line graph, and this is quite simple. You create a tensor network object, which is internally how things are stored, and you get the line graph. And if you want to use orderings from Qtensor, you use ordering optimizer, which is a greedy optimizer. It just selects the smallest degree node. It is very fast. It is a baseline. It is silly fast, and usually for QA, since you have large number of circuits that you want to simulate for each edge, you in fact simulate a different circuit. For that, you will need to optimize quickly. And here is how you get a tree width and elimination order. There is a technique called slicing, which is, I think, beyond what we want to cover in this tutorial. But there is an optimizer that allows you to fit a large circuit to a memory. And let's just wrap up. How do we use the Qtensor? First, let's say we create ansatz circuit. For that, we generate our graph, and then we create a composer object. And the composer works in that way. It is a stateful object, and you apply an ansatz state method to this composer object, and then you can just grab your circuit. And so don't worry about these provider things. I will show what this does later. This is just a helper utility. And if we want to find, let's say we're interested in how complicated our tensor expression is, we use some ordering optimizer, or we can use another optimizer, which is called without optimizer. Without optimizer is special. It doesn't do any simplifications. It just contracts indices in the order that they were created. And you can get the tree width by accessing the optimizer.treewidth. So let's see at some interesting graphs. So this is a helper utility that allows you to plot the values on the Cartesian product of your input variables, and you just specify that p equals 2, 3. Let's say we are interested in p equals 2 and 3, ordering algorithm greedy and without, and just comparing those two algorithms is very interesting, because for different p and for different p, you get the different results. Greedy algorithm is not doing very good for larger p's, but in fact, if you go p equals 3, it will be worse than without optimizer. And without optimizer pretty much returns you how the same tree width as number of your nodes. And I believe this is what I have time to tell you. And the key takeaways is that a small number of p means that you have small circuits, and you can simulate very large graphs in seconds. Large number of p means that you have exponentially larger circuits, and this means that you have exponentially larger amount of memory required to simulate. So they are time-consuming. And the interesting thing is that the complexity of simulation is not monotonic with respect to the graph size that you use. Thank you for your attention.